Welcome to e-partial lecture series on computer science. We are discussing on the paper Cryptography and Network Security. In this module, we are going to discuss about Chinese remainder theorem CRT. To learn about the CRT and their application in cryptography, discuss about Chinese remainder theorem and the algorithms, and also various examples related with Chinese remainder theorem. Chinese remainder theorem was developed in 3rd century by Chinese mathematician Sun Chu. So, here this theorem plays a very important role in the field of cryptography. Whenever if you want to solve a set of congruence equation with one variable but different modeling. So, CRT is used to solve set of congruent equation with one variable but different modeling. And a very important thing is which are relatively prime. So, we know what is relatively prime. So, relatively prime means where the GCD of these two numbers must be equal to 1. If I take two numbers, then it must be 1. So, CRT is where you need to solve set of congruent equation. So, let us see the congruent equation. So, x congruent to A1 mod M1, x congruent to A2 mod M2, like that it goes up to x congruent to A of k mod Mk. So, what we can able to understand here is, according to the statement given for this particular theorem, a set of congruent equation. So, here we have set of congruent equations and different moduli, that is the modulus of the first equation is M1, second equation is M2, like that it goes up to k equations. And also this M1, M2, M3, M4, like that it can go. The GCD of M1, M2, M3, Mk must be 1, then we can say they are relatively prime. So, when I have on the left hand side with one variable, so x as one variable, where I have a different moduli and they are relatively prime, then in that case we can able to solve this kind of equation with the help of Chinese remainder theorem. So, before going to that particular theorem, let us understand a story about an old woman with a eggs. So, here an old woman goes to a market with basket of eggs. When set of baskets down and horse accidentally stepped on it, crushes all the eggs. The rider offered to pay her for the damage of eggs and asked her how many eggs did she have. So, what is the thing here? An old woman going to the market with basket of eggs, accidentally the basket down, it's fall down, and the horse was stepped on it. Now, the rider is ready to pay for her damaged eggs. Now, he is asking that old woman, how many eggs you have in your basket? This is what we need to find it out as x. So, how many eggs? She tells the rider that she cannot remember. So, she didn't know what is the inside, how many number of eggs she had at the time when it is being in the accident. So, but she is giving some riddle, that is, when she had taken all the eggs out 3 at a time. Now, we have to carefully note down 3 at a time where there is 2 left in the basket. So, when she take all the eggs, each time she take 3 eggs, first time 3, second time 3, third time 3, like that. If she took each and every time if she take 3 eggs, then the remaining will be 2. Similarly, the other case what she is telling us, she took them out 5 at a time, there were 3 left. Similarly, another possibility what she is telling us, when I take 7 at a time, there will be 2 left. So, now the question is, rider is ready to pay for her, but she did not remember how many eggs were there in the basket, but she has an idea that when I take 3, I left with 2, when I take 5, I left with 3, when I take 7, I left with 2. So, the question here is how to solve it. That means what is the smallest number of x she could have. So, how to solve it? This problem can be solved with the help of Chinese remedy theorem, because we have different moduli, but what we want to find out here is x. So, when I take a mod m1, then I will get x. Similarly, a2 mod m2 I will get x, ak mod mk I will get x. So, these are set of equation. So, according to this story, how to get to know about how many x the rider need to pay to that old woman. So, let us refer this story with respect to our Chinese remainder congruence equation, where we can refer to first case as per her statement. When I take 3 at a time, I left with 2. So, now we can say that a1 is 2 and m1 is 3. Then what is x? We do not know. Similarly, when I take 5 at a time, I will get 3 as remaining in my basket. So, we do not know what is x. Similarly, if I take 7 at a time, I am left with 2, I do not know what is there in the x. So, now our idea is to get this x value. So, for that purpose only we have one theorem which is going to be understood with the help of mod operation. So, we know what is mod of n. What does mean mod of n? So, always in your Chinese remainder theorem we use the modular arithmetic of m, where it will give the remainder. Here a is congruent to 1 mod of m1, it says that a is equal to x. So, when I am using a mod of m1. So, Chinese remainder states that the above equation have an unique solution if the moduli are relatively prime. If the moduli are relatively prime, then we can have a unique solution to find out what are the set of congruents. So, let us work with an example before going to solve that particular riddle. We should also know about how to solve, right. So, as here the following is a set of equation with different moduli 3, 5 and 7. So, you have 2 is remainder after mod of 3 is congruent to x. So, x congruent to 2 mod 3, x congruent to 3 mod 5 and x congruent to 2 mod m. So, in this the solution to the set of equation is given in the next section. For this moment, note that answer of this set of equation is 23. So, we can guess it, right. If I say this is going to be x is 23, then mod 23 mod 3, what is the remainder? It is going to be 2, yes. Similarly, if I take the 3 mod 5 is equal to 23, then 23 mod 5 is equal to 3. That means 23, when I am dividing 5, I will get the remainder as 3. So, I will say that 23 mod 5 is 3. Similarly, 23 mod 7 is 2, because 3 7s are 21, the remainder is going to be 2. So, now we got the answer for that story, that is actually the x is equal to 23. That means that the x was inside the basket were 23. So, the rider has to pay the amount 23 x. So, we will come to know how we got 23, right, how we got this 23 with the help of your Chinese remainder theorem. So, the steps involved in finding the common value x, there are 4 steps are involved. In the step 1, first thing what you have to do is a capital letter m, which is nothing but common modulus. So, according to the set of congruent equations where we have 1, 2, 3, here m1, m2 and m3. In general, what we can say here is m is equal to m1 into m2 into m3 into, like that it goes up to mk. So, first step what we have to do is we need to find the capital M, which is multiplication of all the modulus in the congruent equation. The next step what we have to do is we need to find m1, that means capital M1, which is different from smaller m1, that is capital M1 is equal to capital M divided by m1. Similarly, we have to find out for m2 capital M divided by m2, like that we have m3 capital M divided by m divided by m3 smaller m3, then like that we do till mk is equal to capital M divided by mk. So, this is the second step. So, first we need to find out the common modulus. That means, what is this case? We have to multiply 3 into 5 into 7. Then after getting the value, then we have to divide it by m1, m2, m3 to get m1, capital M1, capital M1, M2. Like that is the step 2. Then the step 3, find the multiplicative inverse of m1, m2, m3 and mk using the corresponding moduli m1, m2, smaller m1, smaller m2, which is nothing but we call here as inverse of capital M1, inverse of capital M2, inverse of capital C. So, the third step will help you to find out multiplicative inverse of each and every modulus which is dividing the common modulus. We are going to get the individual modulus. Once we got it, the last step is to find out the value of x. So, that is given by x is equal to a1 into m1 into m1 inverse plus a2 into m2 into m2 inverse, like that, ak into mk into m inverse mod m. So, we can understood here, if I want to solve for getting the, so that is what we are saying in the case of your Chinese Riemann theorem. Here set of congruent equation with one variable but different moduli. So, x is our one variable. Now, we can able to understand here this x can be obtained with the help of these 4 steps by getting the common modulus. From the common modulus I am getting the individual modulus, and then I am finding the multiplicative inverse of this modulus, and finally x is equal to a1 into m1 into m1 inverse plus a2 into m2 into m2 inverse, like that, m3, m4, a3, like that we do, and finally we have to do the capital M, mod of capital M. So, if we are able to understand these 4 steps, we can able to find out the common variable with the different modeling. So, the set of equation can have the solution even if the modulus are not relatively prime, but meet other condition. But in the case of cryptography, the only interest is solving with the co-prime modulus. So, in CRT we say that only we want to work on co-prime or relatively prime. It is not necessary, even if the condition is not met. It is also, this equation will also work for some other value, but in the field of cryptography, when I want to work with a CRT, definitely I should make sure that all the moduli are co-prime to each other, relatively prime modulus. So, now we will find out the solution how we got, right, for the particular example. This solution to simultaneous equation is, we follow the 4 steps as we already know here. X is equal to 2 mod 3, x is equal to congruent 3 mod m, x is equal to congruent 2 mod 7. So, the first step we have to find out the capital M. M is equal to 3, that is your moduli of 1, first equation, second equation, third equation. 3, 5 and 7 is equal to 105. Then what we have to do? We have to find out capital M1 with respect to smaller m1 based on the answer we obtained in the step 1. So, from the step 1 we got 105, that is where we can say m1 is equal to 105 divided by 3. So, now we got 35. Similarly, m2 is equal to 105 divided by 5, because here m2, smaller m2 is 5. So, 105 divided by 2, 21. Then m3 is equal to 105 divided by 7, that is 15, smaller m3. And now this step where we are supposed to find the multiplicative inverse, already we have discussed about the multiplicative inverse. So, what do you mean by multiplicative inverse is, when I am taking this 2, then when I am going to taking this 35 inverse is equal to 2, that means these 2 value will provide me the identity element. Then I can say this can be easily solved with the help of mod 3. suppose I am taking 2 into 35, that is I am going to get 70, 70 mod 3 I will get 1. So, now when I am multiplying these two value and finding the mod of operation, if it is equal to 1, then I can say it is 2 is multiplicity inverse of 35, similarly 35 is multiplicity inverse 2. Similarly, we can also find it for the second element, the multiplicity inverse, where if I take 21, what is the multiplicity inverse of 21? That means I can say 21 into 1 mod 5, if I am getting it 1, then I can say 1 is multiplicity inverse of 21, then 21 is multiplicity inverse 1 with respect to the mod of 5. Similarly, I will do it for the 15 also. So, what we can do here is we have to use some Fermat theorem, or we can use the Euler's theorem, directly you can get your multiplicity inverse, or we have to go for doing them one by one, that is iterative method to get actual multiplicity inverse of the number which is given. So, once we got that multiplicity inverse, we know very well we need to substitute in the final step to get the value of x. So, here x is equal to a1 into m1 into m1 inverse. So, a1 is the value here is 2, and we already found the value related with your common modulus, that is m1 with respect to m smaller m1 is 35, then the multiplicity inverse what we got is 2. So, 2 into 35 into 2 plus, similarly I go for the next equation a2 m2 then m2 inverse, then the third value 2 a3 then m3 inverse. So, once I do the multiplication of this value, which is equal to 23 mod 105, where the 105 is the common which you obtain in the first step of your theorem. So, after multiplying these values, we will get a value which need to be divided by 103 to reduce it to get the remainder of the value, which is nothing but 23. So, now we got the answer, as already we have guessed here, this is 23, it is possible to have 23. Now, we have proved with the help of your Chinese remainder theorem, then the answer is 23 when we have a congruent set of congruent equation in such a way. So, the egg problem, again the same steps we know, right, x, let m is equal to 3, 5 and 7, 105, the same value, and we are getting the multiplicity inverse, then we are substituting here the same value, and we know 233 is the value mod 105. So, we got 23, the answer is totally the old lady had 23x. So, the proof related with your Chinese remainder theorem here is, let s and t be the positive integer with the GCD s and t is equal to 1. What does that mean here is, as I mentioned, s and t are the co-prime, that is relatively prime. When I am taking the first value, for example, here in this equation 3 and 5 or 5 and 7, then I am trying to find the GCD of 3 and 5 or 5 and 7. Let us take s is equal to 3 or t is equal to 5. Similarly, if I am going to take s is equal to 5 and t is equal to 7, then I should get 1, then I say it is going to be a co-prime. So, it proves that there exists an integer w such that means here it is talking about an inverse multiplication, multiplicative inverse with respect to the number which is given, SW is equal to 1 mod t. So, it proves that when I want to say a GCD of s comma t is equal to 1, it proves that there exists an integer w such that SW is equal to 1 mod t, and for each k let mi is equal to m divided by mk, where we say here m is the product of m1, n2, m3, that what we found out. Then it proves that the greatest common denominator of mi and m smaller mi is equal to 1. That means mi and smaller mi, capital Mi and smaller mi are co-prime to each other. So that is what we say in the case of your cryptography, where whenever I am choosing the set of congruence values, it must have the co-prime or relatively prime to the model, relatively prime model, where you can able to substitute that particular information. The next comes the integer. So as we started with congruent equation saying that GCD and how it is going to be having the prime, co-prime, there exists an integer w such that SW is equal to 1 mod t. Then also we have proved that when I have each k, let mi is equal to m divided by mk, there m is the product of this, and also we say that proves that the greatest common denominator of mi and m is equal to 1, that m1 and mi are co-prime, and also it proves that there is an integer xi such that mi of xi is equal to 1 mod mi, and if there is an ai as an integer, mi ai mi xi is equal to af mod mi. So let x is equal to a1 m1 x1 plus a2 x2 m2 an mn xn. It proves that x is equal to ai mod of, so here x is equal to ai mod of mi. That is what we can able to understand from this expression. As we are discussed about the Chinese remainder theorem, what are the applications are related with this theorem in the field of cryptography or in the field of computer? As we say, this algorithm is used in coding theory, where it detects and corrects the error is done by adding redundancy to the data that is sent via noisy channel or in a computer. So in the code theory, it is detecting and correcting of error. How it is done? By adding the redundant data. So we understood that it is going to be a noisy channel. With the help of added redundant information of data, where this theorem, with the help of this CRT, we can able to detect as well as able to correct the error during the transmission. And CRT reminder techniques are useful in developing the code that detects the error. So when the data is transmitted over a channel, if some bits are modified, this algorithm is able to help to find the errors that may happen during the transmission. In the field of cryptography, where the CRT is used in secret sharing through error correcting code. So when I have a group of people want to have a secure communication, then with the help of CRT is used in secret sharing through the error correction. And CRT itself a secret sharing scheme without need of any modification. So we can able to understand the application wise, this is used in the case of your secret sharing through error correcting code. So CRT is itself a secret sharing scheme without any need of modification. That means I don't want to modify any component of that particular algorithm directly. I can use it for sharing the secret information in the case of cryptography, in the field of cryptography. So as we conclude here, we understood, also we know about what is the Chinese remainder theorem and also what is their application in the field of cryptography. And here we also discuss about the steps involved in the CRT theorem and how we can able to get the common variable using different moduli, and also we have worked with various examples. One of the example of X story with respect to the Chinese remainder theorem. Thank you.